Hello everyone, hope that you have been doing well. As you can see on the screen, our topic today is stresses in soil due to surface loads. Here we go. Any engineering structure built on a soil mass will induce stresses in it. The stresses produced in this way depend on the stress strain characteristics of underlying soil. And a realistic approach is difficult because these properties are not linear. Results from the theory of elasticity are commonly used in practice. It is presumed that the soil is semi-infinite, homogeneous, and isotropic, and that there is a linear relationship between stress and strain. A semi-infinite mass is bound on one side and extends infinitely in all other directions. For soils, the horizontal surface is bounding side. The question is, if soils are not elastic materials, then why do we have to use elastic methods of analysis? Well, an elastic analysis of an isotropic material includes only two constants, namely Young's modulus and Poisson's ratio. And therefore, if we presume that soils are isotropic elastic materials, then we have a powerful but simple analytical way to predict soil's reaction under loading. We will ought to determine only the two elastic constants from our laboratory or field tests. It is important to note that a stress strain relationship is almost true when the stress levels are low with respect to failure values. The adoption of elastic theory obviously includes considerable simplification of real soil behavior, and it must be kept in mind that the results obtained in this way are only approximations. The stresses at a point owing to more than one surface load can be obtained by superposition. We will have an example for this case later on. Negative values of loading can also be used if the stresses as a result of excavation are needed. The stresses owing to surface loading act along with the in situ stress because of the self weight of soil. As shown in the figure, sigma sub V is due to self weight of soil, and delta sigma sub V is due to surcharge loading placed on the ground surface. Surface loads are categorized into finite and infinite. Examples of finite loads are point loads, circular loads, and rectangular loads. Fills and large surcharges are examples for infinite loads. The relative rigidity of the foundation to soil mass affects the stress distribution within it. Therefore, the elastic solutions presented here are for flexible loads and do not take into account the relative rigidity of the soil foundation system. Equations for several types of flexible surface loads based on the assumptions mentioned earlier are as follows. I don't want to get you bogged down in details about the derivation of these equations. Instead, I will show you how to use them for the case needed, giving you striking examples. The first case is the vertical stress increase due to point load. Buchanan produced a solution to find normal stresses at any point within the ground due to point load applied on the ground surface. Now, with the help of equation produced, we can calculate stress increase at any point just beneath the load or at some distance away from the center of point load. An example of point load is the vertical load transmitted to the soil from a column of single foundation or an electric power pole. It is possible to draw the variation of stress increase vertically and horizontally, as shown in the figure. As we go down or away from the center line of point load, the stress intensity decreases. Now, let me give you a practical example. A meter square foundations of 3 parallel electric power poles exert point loads of about 500 kilonewton at the foundation level as shown in the figure here. Now you are asked to determine the increase in vertical stress at point A, as shown here, which is 2 meters below the base of foundation. In the solution of this problem, the first step is to use the equation for a point load. And the second step is to calculate the vertical stress increases from each foundation at point A. These are already done for you. In the equation, we know the value for point load and the depth of point under consideration. We just need to calculate R for each case as illustrated here. The total stress increase at point A will then be the summation of each stress increment. Loads and rail traffic loads and loads from walls may be regarded as line loads. They have length along a given line, as shown in the figure here, and no breadth. Of course, this is a theoretical assumption. The vertical stress increase from a line load in this case can be calculated by this equation given here, where Q is the line load acting on the ground surface, and Z is the vertical distance of point A under consideration, and X is the horizontal distance as shown in the figure. A practical example for this case is given in the figure here. This figure shows 2 line loads on the ground surface, one from a train and the other from the wall. You are required to determine the stress increase at point A above the tunnel roof as shown here. Similar to previous example, the first step is to use the equation for a line load, which is given here. And the second step is to calculate the total vertical stress increase at point A under consideration. To do this, we need first to calculate stress increments from each case. One from train as given here and the other one from the wall. So the total stress increase at point A will then be the summation of each stress increment. A strip load is transferred by a structure of finite width and infinite length on a ground surface. Continuous footings are those whose length is very long compared with their breadth. The other two types of strip loads prevalent in geotechnical engineering are the middle section of a long embankment, as shown in the figure here, which exerts a uniform stress on the soil, and the sides of the embankments with triangular stress distribution. Stress increase due to triangular stress distribution at any point within soil mass can be obtained using these equations given here. On the other hand, stress increase from uniform stress distribution at any point within soil mass can be obtained using the equation presented here. In these equations, the values of angles alpha and beta can be determined from the cross-sectional dimensions by using simple trigonometry. What is important in here is that alpha should be used in the equations as radians. Vertical stress increase from an embankment loading can be determined by the equation presented here. In this equation, Q is equal to gamma times H. Gamma is the unit weight of the embankment soil. H is the height of the embankment. Alpha sub 1 and alpha sub 2 are the angles as shown in the figure. They can be obtained through simple trigonometry and used as radians in the equation. It is important to emphasize here that if large fills and surcharges are placed on the ground surface, then the loads from them are assumed to be transferred to the soil as a uniformly distributed vertical stress. For example, if a fill of unit weight 18 kilonewton per cubic meter and height 2 meter is placed on the ground surface, then the vertical stress at any depth is equal to 2 times 18, which is 36 kilopascal. Practical example for this case is the planned road embankment as shown in the figure. You are required to determine the stress increase at depth Z just beneath the midpoint of the embankment. Given are the unit weight of embankment soil, height of embankment, crest width of embankment, and the depth under consideration. The first step is to determine the stress imposed by the embankment on the soil surface, which is equal to unit weight of embankment soil times the height of embankment, and this is around 123 kilopascal. In the second step, we need to figure out the angles of alpha sub 1 and alpha sub 2. To do this, we first need to determine B2 from the figure. B2 is the side width of the embankment as shown in the figure. Using the slope inclination as given here, the slope angle can be obtained as 27 degrees. Depending on these, B2 will be 14 meter as illustrated. To use the related equation mentioned earlier, it is vital that we need to divide the embankment in two equal parts as shown in the figure, and then figure out the stress increments from each one at depth Z. Based on the widths of embankment, which are B sub 1 and B sub 2, and the depth Z, we can easily compute the angles of alpha sub 1 and alpha sub 2 as illustrated. In the final step, we need to calculate the stress increase at 5 meter depth below the midpoint of the embankment. Now, we have all related values. If we put them in their places in the equation as shown, we get the stress increment from the 1/2 of the embankment at depth Z. If we double it, we get the stress increment from the whole of the embankment, which is around 110 kilonewton per square meter. That's it. Many structural foundations are rectangular or nearly rectangular in shape. The solution for the increase in vertical stress at any point below a corner of uniformly loaded rectangular area, as shown in the figure, is computed using this equation, in which Q is the pressure acting on the ground surface. L and B are the length and the width of the loaded rectangular area. Z is the depth at which the stress increase is needed to be calculated. R sub 1, R sub 2, and R sub 3 are the dependents of L, B, and Z as shown. The benefit of suggesting a solution for a corner point is that stress increase can readily be computed by superposition for any point in the ground due to any uniformly loaded area, which can be subdivided into rectangles. For example, under the point A in the figure, the stress increase due to loaded area is determined by dividing the rectangle into smaller ones and determining the stress increase beneath the corner of each rectangle and then combining them. Similarly, under point C in the figure, the stress increase due to loading can be obtained by determining the stress increase beneath the corner of uniformly loaded big square area, which is B times B, and subtracting from it the stress increase beneath the corner of the uniformly loaded small square area at point C. Practical example for this case is a building with mat foundation stands on the surface of a soil mass as shown in the figure, and the load on the foundation is 89,250 kilonewton. Determine the vertical stress increase at a depth of 3 meter at point A under the center of mat foundation and at point B at a distance of 1.5 meter from a corner as shown in the figure. Now, in the solution of this problem, the first step is to divide the rectangular mat foundation so that the center is a corner. In this way, 4 equal rectangles are obtained. At this stage, point B is excluded for simplicity. So we only have to find the vertical stress increase for one rectangle and multiply the result by 4. We now move on to the next step to find the vertical stress increase below the center of the mat foundation at point A. Before that, contact pressure, the pressure at the base of foundation, should be determined. It is the ratio between the total load acting on foundation and the area of foundation, and it is 150 kilopascal. R sub 1, R sub 2, and R sub 3 can be easily computed based on the length, width of the rectangle and the depth of point under consideration. Having all these values, we put them in their places in the equation as shown, and we get the stress increase beneath the corner of one of those 4 equal rectangles. If we multiply this value by 4, then we get the stress increase at point A beneath the center of mat foundation due to foundation load. In order to find the stress increase at point B, we need to extend the rectangle to be as shown in the figure, and then find the stress increase for the large rectangle. After that, subtract the stress increase for the smaller rectangle, which gives us the stress increase at point B outside the mat foundation. For large rectangle, we need to calculate R sub 1, R sub 2, and R sub 3. They are already done for you. And if we now put all these values in their places, as shown here, we get the stress increase from the large rectangle, which is 37.44 kilopascal. If we follow the same procedure for small rectangle, we obtain the stress increase at point B as 35 kilopascal. As emphasized earlier, the difference between two values will give us the stress increase at point B, which is outside of the mat foundation. Is there any simple method for the analysis of vertical stress increases under the center of rectangular loads? Well, geotechnical engineers generally use an approximate method. It is also called 2-1 method, to analyze the vertical stress increases under the center of rectangular loads. The surface load on an area B times L, as shown in the figure, is dispersed at a depth Z over an area B plus Z times L plus Z. So the vertical stress increase in this case can be obtained by the equation provided here. Considering example 3, let us now compute the vertical stress increase under the center of mat foundation at point A using 2-1 method. In the equation here, Q is the foundation load acting on the ground surface, and B plus Z times L plus Z is the area at depth Z. This gives us 117.43 kilonewton per square meter stress increase, which is about 25% less than the elastic solution. Vertical stress increase at depth Z beneath the center of uniformly loaded circular area can be determined with the help of this equation given here, in which Q is the uniform pressure acting on the ground surface, R is the radius of circularly loaded area, Z is the depth of point under consideration where the stress increase is needed to be calculated. An example of a circular area is a circular foundation of an oil or water tank. Here it is, an example for the case of uniformly loaded circular area. A water storage tank, 15 meter in diameter and 10 meter in height, is recommended for a site where there is an existing wastewater pipeline as shown in the figure. You are asked to plot the distribution of vertical stress increase enforced by the water tank on the wastewater pipeline and comment on the result you find. The dead weight of water storage tank is 350 kilonewton, and assume that the water tank is filled to its capacity. Let us solve this problem together. The first step is to compute the total load acting on the ground surface owing to water tank. For these, we need first to determine the volume of water in tank, which is equal to pi times r squared times h. R is the radius of the storage tank, h is the height of the tank. Then the weight of water can be obtained by multiplying the volume of water in tank and the unit weight of water. The total load on the ground surface will then be the summation of the weight of water in tank and the dead weight of the water tank. Therefore, the pressure acting on the ground will be the ratio between the total load acting on the ground surface and the cross-sectional area of the storage tank. The second step is to determine the vertical stress increases with that. Using the equation provided here, stress increments at each depth can be calculated. After tabulating the test results as shown here, the final step is to draw the distribution of vertical stress increases with that. As you see from the figure, there would be a seizable stress increase on the pipeline. So the strength of pipe material should be checked if it is sufficient or not. If points of equal vertical pressures are drawn on a cross-section through the foundation, a diagram of the form shown in the figure here is attained. This diagram is known as bulb of pressure and form another way of determining vertical stresses at points below a foundation for regular shapes. The curves point out the values of delta sigma Z over Q beneath the footing, where Q is the uniform footing pressure. The horizontal extent of the pressure bulb also displays how pressure from one foundation can apply additional stress to soil under an adjacent foundation. For example, building a heavy structure close to an existing one can contribute to adverse settlements of a nearby corner of the older structure. We may plot any number of isobars for any given load system, but the one that is of practical importance is the one which includes a soil mass which is responsible for the settlement of the structure. The depth of the stressed zone may be called as the significant depth, and most of the settlement, about 80% of the total settlement, occurs at a depth less than the significant depth. A stress contour, which represents 20% of foundation contact pressure, as shown in the figure, is considered the significant depth for all practical purposes, because the stress increases beyond this point are considered negligible. The significant depth is approximately equal to 1.5 times the width of footing as shown in the figure. In the figure above, you see the effects of both foundation, breadth, and grouping. As the soft stratum below footings is not stressed by a single foundation, it is included within the significant depth by the combined effect of the adjacent single foundations. These tell us that we should place the foundations at a clear distance from each other so that their isobars do not collide. Final example to show you how to use the bulb of pressure chart. A 1 meter square foundation of new building, as shown in the figure, will transmit a pressure of about 100 kilonewton per square meter at the base of foundation. Accordingly, what will be the increase in vertical stress in the middle of the soft layer at point A, which is beneath the center of the new building foundation? B, what influence would these have on the existing building foundation that is 1.8 meter away from the center of the new foundation? The first step to solve this problem is to determine the ratio of delta sigma Z over Q under the center of new footing. What we know is that the depth to center of the soft layer is 1.5 times B. B is the width of the foundation as shown in the figure. Notice that the horizontal and vertical distances are arranged in terms of width of footing. So, from the figure, delta sigma z over q is obtained as 0.20 under the center of new footing. The second step is to calculate the vertical stress increase under the center of new footing. This is easy because we have the ratio. If you multiply this ratio by the contact pressure of foundation, which is 100 kilopascal, then we get the stress increase as 20 kilopascal. The final step is to determine the stress increase under the existing foundation. We know that the center of the existing footing is 1.8 times B from the center of new footing. So from the figure, Q is about 0.019 at a depth of 1.5 times the width of new footing. The stress increase in this case under the foundation will be the ratio just obtained multiplied by the contact pressure, which is 100 kilopascal. So the stress increase will be 1.9 kilopascal. This will have only a moderate effect on the adjacent foundation. I'll give you a quiz on what you have learned so far. The stress increase due to surface load depends on the stress-strain characteristics of underlying soil. True or false? It is true. Good. And the second one, soil's characteristics are linear. True or false? Yes, it is false. Very good. Keep going. The stresses at a point owing to more than one surface load are obtained by superposition. This is also an easy and peasy one. What? Yes, well done. It's true. And the fourth one, road and railroad loads and loads from walls are examples of line loads. True or false? No, you got it wrong. It is true. The stress increases below a surface load are found by assuming that soil is inelastic and semi-infinite mass. True or false? It is true. Jolly good. The stress increase at any depth is independent of the shape and the distribution of the surface load. True or false? No, it is false. I'm not saying dependent of the shape, independent of the shape. So the answer is false. A stress applied at the surface of a soil mass by a loaded area decreases with depth and lateral distance from the center of the loaded area. To answer these, you should visualize the pressure bulb or just look at the figure in front of you. Which one? It is true. Very good. The vertical stress increases are generally greater than 10% of the surface stress when the depth to width ratio is greater than 2. Again, look at the figure of pressure bulb and then state whether it is true or false. No, it is false. Look, it is said the vertical stresses are generally greater than. If it was like this, the vertical stresses are generally less than 10%, then your answer would be true. So in this case, the answer is false. Constructing a heavy building close to an existing one may contribute to its detrimental settlement. True or false? It is true. Very good. Examples of infinite loads are point loads, circular loads, and rectangular ones. True or false? It is false. You are the man. 20% of the foundation contact pressure is considered the significant depth for all practical purposes. True or false? Yes, it is true. You got the point, man. And finally, the significant depth is increased by the combined effect of the adjacent foundations. True or false? It is true. Congratulations. That completes my lecture. Thank you for listening. Have a great day. Hope to meet you again.